Okay, we're going to lay a little groundwork for how building mechanical systems use energy. Because what we learned in our end-use breakdown is that well over half of the energy in a building is used by the mechanical systems. So when we understand how they interrelate, it affords us the opportunity to optimize them and build energy efficiency into the building. So let's say we have a building and it's got a couple of floors, a couple of different size spaces, maybe a giant conference room in the middle. And we need to heat and cool the building. So the building is equipped with an air handling unit that is typically located on the roof, or at least for our purposes, we'll say that the air handling unit is located on the roof. And it's got a big fan, which we learned about again in our end-use breakdown. This is one of our big building energy users, is the fan. And the fan is responsible for delivering air to all of the spaces. So there's ductwork that runs through the spaces to each floor. It branches out. There are individual runs to each space. And then each space is equipped with a piece of equipment called a VAV box. And we'll talk about that a little bit. I'll show you some pictures in real life here. A VAV box has a damper in it, and VAV stands for variable air volume. So there's a little damper in there, and that controls the airflow that's ducted out to the diffusers in the space. So the diffuser is what you see in the ceiling when you look up. So there's diffusers that are delivering air to the space, and this damper controls the airflow. If you need more cooling, it'll deliver more air to the space. And then we'll talk about heating in a second. But basically every one of these spaces in the building has a VAV box. The little damper. And then on our top floor, we'll install a VAV box. We'll keep that one simple. So that's what's delivering air to the space. Now the air needs to recirculate, so there is a return air system, and typically each floor has a collection plenum and a shaft runs up through the building that returns the air to the air handling unit. And we'll just say, for this simplicity, that the air is coming in the bottom of the air handling unit through a set of dampers so that its volume can be controlled. So that's how we get air to the space. That's how it's circulated. Now, what about cooling? Because the whole point of this air handling unit is that we're able to cool the spaces. So cooling is provided by a coil, a chilled water coil, in the air handling unit that is piped from the chiller plant. And here enters another set of mechanical equipment that's commonly located in the basement, or maybe for our purposes, we'll say that there's a central utility plant. They often call it a CUP. Central utility plant that houses the chillers. So this is another side building that houses the chillers. So in this building, we've got a chiller. And the chiller is delivering cold water. I didn't make my building big enough. So engineering flaw. So there's a pump that's pumping water through the chiller to make cold water, and it is being distributed to the air handling units in the building. On a large campus, you could have up to 20 or 30 air handling units. But the water's delivered to this coil, and then the coil has a control valve so that it can modulate how much to water it needs depending on the load in the building. And then the water is circulated back to the central utility plant. So again, here's one of our pumps, one of our energy users in the building. Chillers making cold water. This is typically making 44-degree water, pumped all the chill water coils, controlled by a control valve, and returning to the central plant. So the other piece of this cooling system is that this chiller is providing cooling to the building, but then it needs to be cooled. So there's a device called a cooling tower, which you see all the time outside of buildings. We'll put this one on the roof. The cooling tower has another set of pumps. The pumps water through the condenser side of the chiller up to the top of the cooling tower. It's sprayed over the fill, it cools, and then it is returned to the chiller. So this cooling tower loop has a pump, a cooling tower fan, and it's providing the cooling to the chiller, essentially to the whole building. But that's your cooling system.
I remember when I lost my mind. There was something so pleasant about that place. Even your emotions have an echo in so much space. And when you're out there without care, yeah, I was out of touch. But it wasn't because I didn't know enough. I just knew too much. Does that make me crazy? Does that make me crazy? Does that make me crazy? Possibly. And I hope that you are having the time of your life. But think twice. That's my only advice. Come on now, who do you think you are? Bless your soul. You really think you're in control? Well, I think you're crazy. I think you're crazy. I think you're crazy, just like me. My heroes had the heart to live the lives I wanna live, and all I remember is thinking I wanna be like them. Ever since I was little, it looked like fun.
So
If there's no coincidence.
that's how we maintain cooling in the building. And how about heating? Because what we learned in our end use breakdown is that heating is the largest energy user in the building. So in the central utility plant, we've got a boiler. And this boiler is typically making steam, and the steam goes to a heat exchanger, and then that makes hot water. And the hot water is pumped to, as you can imagine, the air handling unit through a coil to provide heating if the air handling unit needs heating. And it too has a control valve to say, yes, I need heating, no, I don't, or how much heating do I need? That modulates volume of flow. And then that water is circulated back to the heating plant. So again, we've got a pump delivering hot water. Now the important thing to note about how buildings are heated is that the heating typically occurs actually at the space level. So while this pump is delivering hot water if necessary to the air handling unit, the more important thing is that hot water is piped to every floor of the building, to every space of the building. So this hot water line has a little coil in this VAV box. So there's a heating coil and a valve in every VAV box on every floor in every space of the building. So this VAV box is controlled by the thermostat on the wall. So this is where the mechanical systems meet the user. The thermostat controls that VAV box. So when you're in a building, every time you see a thermostat in an office or on a wall, what it's doing is it's controlling the VAV box in that space, and it's telling the VAV box either I need to open up the damper to provide more cooling, or if the space is too cold, it says I need to close back the damper a little bit and open up the heating. So the heating in a building really happens at the space level, and we call it reheat. Now let's go back to the air handler for a second and talk about what the air handler is doing and why we call this reheat. Typically, the job of this air handling unit is to provide cooling. So it's typically configured to deliver 55-degree air. So its job is to make 55-degree air, and that's what's distributed through the ductwork. So you can imagine if a space needed cooling, if you delivered 55-degree air, that would provide appropriate cooling. If a space needed heating, you would have to take that 55-degree air, heat it up to at least room temperature and more than room temperature if you wanted to provide heat. So that's an important thing to think about. Really, the common system that we see in buildings is this variable air volume with reheat.
Be the charming type. Take off your gloves and show what they hide. Please, please my naked wrist with your hands and fingertips. And please, baby, get on your knees. Don't bare your teeth. I'll let you cry if you close your eyes. Why be the charming kind? Oh, you'll get yours when I get mine. Oh no, it's not for me. If you're too good, you won't be free. And please, please, I'm on my knees. I wanna feel your teeth. I'll get on your knees.
So what we've been talking about here, what we've been learning about, is HVAC. We talked about the AC, that's the cooling. And that uses energy via pumps, chillers, cooling tower fans, condenser water pumps. That's where our cooling energy comes from, also from the fan at the air handling unit. And then heating uses energy at the boiler, and then it uses pump energy to distribute hot water to the spaces. But the thing we haven't talked about yet is the V, and the V is for ventilation. And so an important thing to consider about buildings is that there are people in the buildings. And in some cases, important people. So Betty occupies this corner office here. Betty's pretty important in this organization. So the people need ventilation, and the V is for ventilation. And what that means is we have to deliver fresh air to the building. If we just recirculated air in the building the way we've talked about and heated and cooled, people would be thermally happy, but they would use up all the oxygen and go to sleep. So code actually dictates how much ventilation is required in a building, and that is delivered through the air handling unit. And so what we're going to add here are a set of dampers on the outside. So we'll call this OA, outside air. So this is where outside air is drawn into the air handling unit and delivered to the spaces. So typically there is a minimum outside air rate to meet ventilation needs, and that's usually about 20% of the entire airflow required to provide heating and cooling. 20% of that air should come from the outside. And that's just a rule of thumb for talking purposes here. So we're always bringing in some outside air at the air handler. We're providing cooling, and heating's happening at the VAV boxes.
You never get the paw prints out of the henhouse now, and you can't go back the same way you came. Round all the pieces up, but they just don't hit the same. White knuckles, maybe it's not so bad. So let your hair down now, white knuckles. Yeah, maybe it's not so bad. Oh, go ahead and let it down. Come and let it all out, let it bleed. Did you get what you want? Did you get what you need? I'm behind the lines, behind the wall. Tell me what's the bed you made really that bad after all? White knuckles, yeah, maybe it's not so bad. So let your hair down now, white knuckles. Oh, maybe it's not so bad. Just let it all come down now.
So a couple of features to think about that we'll talk about later when we talk about energy measures is the economizer. And the air handling unit has what we call economizer, or at least we want it to. And the way that works is, if you think about the job of this air handling unit, like we discussed, its job is to deliver 55-degree air. So we've got return air coming back from the building, and that return air is usually about 74 degrees. So we've got about 74-degree air coming back to the air handler. And then we've got this option here for outside air, right? So if you're trying to make 55 degrees and it's, say, 60 degrees outside, what do you think your dampers should be doing in that case? They would be choosing the colder airstream, ideally. So in that case, you would want 100% outside air coming into this air handler, because that means you've got 60-degree air that you have to mechanically cool to 55 degrees, as opposed to having 74-degree air that you have to cool to 55 degrees. So this is what we call an airside economizer, and it basically uses outside air, cool outside air, to replace the need for mechanical cooling in the air handler. So great energy saver will talk about that as a measure and talk about how to identify whether or not that's working in the building. And the other thing to think about with regard to the air side systems is that we're providing this ventilation that we talked about by having 20% outside air always coming into the building when it's occupied. So what if all these people go home? Do we still need the ventilation? And the answer is no, unless there are other driving air change rates because of processes in the building or certain types of spaces. But generally, ventilation in a space is only required when the people are there. So that's an important thing to note in terms of energy use, because that ventilation is causing you to bring in outside air, which can range from 0 degrees outside to 110 degrees outside. And if you have to bring that outside air in, you're going to have to condition it at the air handler or at the VAV box, and that requires energy. And if you don't need to bring that ventilation air in, then there's an energy opportunity. So in review, we've got our building. We call this the air side systems. These are the water side systems. The important thing, perhaps the most important thing that we haven't talked about yet, is that all of these devices are controlled by a computer. And that computer is called the building automation system. And I'm going to highlight automation because that is what we're going for here. This computer has the ability to optimize all of these devices that we've talked about. So from air side systems, this fan control is being controlled by the building automation system. The temperature it's delivering is being read back to the building automation system so that it can in turn control the chill water valve and the heating valve and the dampers. All of these temperatures are being read back. In each VAV box, the thermostat is communicating to the building automation system. So this is telling the building automation system what the room temperature is, what the set point is supposed to be, what this damper position is, what this heating coil valve position is, how much airflow we're getting into each space. So the VAV box is communicating all of its data points back to the building automation system and able to optimize the control. Same thing with the water side. Pump speeds are controlled, temperatures are being read back, the chiller's enabled, the boiler's enabled, the cooling tower fans are speed or commanded. Same with pumps, temperatures on condenser water. So all of these points every minute or two are being communicated to the BAS, as we call it. And that's what affords us a lot of opportunity to make the building smart. So there's our mechanical systems, and with that groundwork, we can embark on energy efficiency opportunities.